Thanks, Hayley, and thanks, Beck. Hi, Jane. Hi, Mandy. Good to see you both. As Hayley was saying, we're going to be talking about the climate, past, present, and future, and just acknowledge some of the contributions from some of my colleagues at the university. And I'd like to talk about two things. First, I'd like to talk about climate of the past, so what we've already experienced, and that includes the importance of climate variability in Australia, and then importantly, how climate's actually changed in the last 100 years or so, and talk briefly about what's caused some of the changes that we've observed. And then the second part of the presentation, I'll talk about the future climate, and I'll talk about what's projected for the decades ahead. And we'll begin by looking globally, and then we'll look at what's projected for Australia, for South Australia, and then for Murraylands. And everything I say tonight will be based on peer-reviewed literature. So that includes reports from the Intergovernmental Panel on Climate Change, which is the world's foremost authority on the science of climate change. We'll also draw on reports from the Bureau of Meteorology and CSIRO, as well as some reports, some really useful reports put together by the South Australian government. So let's begin by looking at the importance of climate variability, which I'm sure you appreciate, but just to highlight it. So just to, and I could show this for anywhere in Australia, but I've picked somewhere near you, hopefully not too far away from there. Actually, if you could, I was going to say, where are you both from? So normally we wouldn't have interruptions, but given there's only two people, maybe if you wouldn't mind letting us know where you are.
So Scott, Mandy here. It's I live in Paringa. Pinaroo is about an hour drive from us, south.
Oh, okay.
Yeah, so I live in the Riverlands, and I work for RDA. So we cover across Murraylands, Riverlands, the region there.
Right, thanks. And
I'm on a farm at Mantung, so I'm not sure if you know where that is. It's probably, an hour. I think it's a couple of hours away from Pinaroo, actually, but yeah.
Right. To sort of north of Pinaroo.
Now you're making me do the thing.
Right.
No. Like just out of Loxton. Do you know where Loxton is?
I've got a map. I'll be showing a map, so maybe when we get there, you can point it out.
Yeah.
Great. Thank you very much.
Yeah. So Pinaroo is basically south to where we are, or
Right.
southeast.
Right.
Yeah.
But I could have chosen pretty much anywhere and it'd say the same story. So what this shows is each bar, each little rectangle, blue rectangle represents how much rainfall fell in that particular year at that location. So in this case, Pinaroo. Get back from 1900 through to 2020. And not surprisingly, there's a huge amount of variability. So in I think it was 1983, the rainfall here was just, the bottom of this graph is 100 millimetres. So in that year, there was just over 100 millimetres of rainfall, whereas in one of those earlier years, can people see my cursor? Yeah, so that's the year I was just talking about then. And then this year here, I think it was 1973. Oops, don't know why I did that. 1973, it was over 600 millimetres. So there's a huge, a factor of 6 almost variability from the least amount to the highest amount. So it's a huge amount of variability. And one of the reasons for that is that your part of the world and much of Australia is heavily influenced by the El Niño Southern Oscillation, and which is a natural phenomenon centred in the tropical Pacific. And the El Niño Southern Oscillation has 3 main phases. The El Niño phase, a neutral phase when not much is happening, and then a La Niña phase, which is, we're actually in the tail end of a La Niña at the moment. And that's been linked to a lot of the heavy rainfall and probably even the humidity, I think, that we've been experiencing in recent times. And it's contributed to some of the flooding that we've seen up north. And tragically also, we find that in the East Coast, coastal floods tend to cause more deaths during La Nina years than El Nino years. So what we've seen is consistent with all of that, unfortunately. And during El Nino, we tend to get more rainfall over so on the plot on the left, that shows a decile map. So all the blues indicate that rainfall tends to be on average during La Nina above average. And then on the right, the El Nino map, it's mostly pinks and reds. That indicates that on average, El Ninos tend to cause a reduction in rainfall. And you can see that in your part of the world, you've got blues during La Nina, and in your part of the world, you've got reds during El Nino. So you're in that respect similar to much of the rest of Australia. And remember, we just looked at this plot for Pinaroo, and we pointed out the low rainfall in 83 and the high rainfall in 73, I think it was. And it turns out that that peak was actually a La Nina year, and that small amount occurred during an El Nino year. So you certainly are influenced by El Nino, La Nina in your part of the world. But of course, El Nino, La Nina is not the only thing that causes rainfall variability in Australia. So another major driver is something called the Indian Ocean Dipole, and that also affects your part of the world. So when, but usually during winter, spring, and usually when the IOD is in a positive phase, then we tend to get less rainfall in your part of the world. Whereas when the IOD is in a negative phase, we tend to get more rainfall in your part of the world. So IOD, Indian Ocean Dipole. And when the IOD, Indian Ocean Dipole, is in a negative phase, you tend to get warmer water to the north of Australia. When you get warmer water to the north of Australia, you tend to get greater rainfall over Australia. Now, I know a lot of people keep track of all of these things, what's happening to El Nino, La Nina, what's happening to the Indian Ocean Dipole and southern annular mode and lots of other different climate modes that affect climate in Australia. But actually, if you're interested in rainfall and temperature, for example, what's going to happen over the next season, the Bureau does all of that for you, and they come up with a single outlook that takes all of those things into account. And so this map on your left, shows what the rainfall outlook looks like for the 3-month period from April to June. So April, May, June, the coming April, May, June. This was issued on the 10th of March, so about a week ago. And what this shows is the chance, or the percentage chance, that the rainfall averaged over that 3-month period will exceed the long-term median. And the median is the sort of halfway mark. So if you look back at all the records, half the years the rainfall was above the median and half the years were the rainfall was below the median. So it suggests that for much of Eastern Australia, you see lots of blues. So there's a slight shift, a pretty weak shift towards an increased likelihood that rainfall will be above the median. And in your part of the world, there's a bit of blue. So it indicates that there's around about a 60 to 65% chance that rainfall averaged over that 3-month period will be above the median, your long-term median. Which, if there was no signal, if there's nothing happening in the climate system, then this would be 50% everywhere. But you can see that there's something going on, but it's not a big thing. So there's a slight shift from 50 to 60 to 65%. And I've zoomed in on your region down here. Actually, is your town mentioned?
Yeah, so for myself, you see where Renmark and Waikerie and that are. So yeah. Paringa is just next to Renmark.
Oh, right.
And
okay.
I'm down here near Karoonda.
Down near where?
Karoonda. Just above the word Barker, you'll see the word Karoonda.
Oh, Karoonda, right,
yep,
right.
I'm right near Karoonda.
Okay. So is your town on the road between Mildura and Renmark?
Correct.
Oh, so I must have been through it.
Yeah.
Sorry, I don't remember it. Sorry.
We're the first town after the Yamba border cross.
Oh, okay. Right. That's not where the guy on the front bar was sponsoring the public bar, or is it?
Yes, it is. That's Renmark.
It is.
Yep, that's us.
Okay. So what then you might ask, well, how does the Bureau actually produce these outlooks? And what they use are climate models, which are similar to, sorry, my arrows aren't working properly, so it's a bit hard to adjust, but anyway. So we use, the Bureau uses climate models, which are mathematical models that encapsulate the physics of the climate system. So they have variables and equations for the ocean. They have symbols and equations for the atmosphere and sea ice and some processes over land. And then they also have equations that govern the way in which the atmosphere and the ocean connect to each other. So if the wind increases, the current increases and things like that. So they're extremely complicated things. In order to, what we do is we break the world up into little boxes and we keep track of how much heat's going in one box and out another. We keep track of how much mass is going in one box and out another, how much moisture. And what we would really love to do is have lots and lots and lots of little tiny boxes, because the smaller we can make the boxes, the more accurate we can make the simulation. But the trouble is, the more smaller you make the boxes, the more calculations you got to do and the more powerful the computer you need to run the model to do the prediction. And it turns out that even the most powerful computers in the world don't enable us to reduce those boxes to the small size that we would like them to be. So so that's one of the reasons why the forecasts aren't as accurate as we would like them to be. And so if we zoom in on your region, we just saw that, so that's how they do it with these mathematical models. And we saw that for your part of the world, Murraylands, the chance of it, can I just refer to it as Murraylands, or you also mentioned Riverlands?
We're Murraylands, Riverland, but we're all one.
Okay, so I'll just say Murraylands and you'll know what I mean. So the chance of above median rainfall for this 3-month period, April, May, June, you'll see it's all that light greeny colour. And if you look at the bar, that's somewhere between 60 and 65%. So the 60 to 65% chance that the rainfall will be above the median. So in other words, it's more likely than not, but it's certainly not, it's not certain. And then the complaint that the Bureau, because I used to work in the Bureau for many, many years, and the complaint we often get is, well, why can't the Bureau be more specific? You know, why can't you give us much greater guidance than this? And the answer is because of chaos theory. So chaos theory, the atmosphere is partially chaotic. So what that means is if you in order to do the predictions, you've got to tell the models what the current conditions are, which we know pretty well now because of satellites and lots of observational methods that we've got, but we don't know it perfectly. We know it better than we probably ever have, but we still don't know it perfectly, and we never will. And the trouble with a chaotic system, or a partially chaotic system, is if you try and predict that system, even if there's the tiniest error in what you start the model off with, it will eventually end up being a really big deal. That's one of the properties of a chaotic system. So small things matter. So you would have heard of the butterfly effect. This is the butterfly effect. But even a butterfly flapping its wings will end up having a huge impact on what the climate model says is going to happen. So you get a wide variety of answers. And so what that means is that in order to communicate that uncertainty, the Bureau always expresses these outlooks in terms of percentage chances. So that's why they can't be more specific, because it's the nature of the climate system. So they're doing the best they can, but unfortunately, the climate system is partially chaotic. There is this degree of uncertainty about what it's going to do. So the best way of expressing that, even though people hate it, is to give it in terms of percentages. Now, so far we've talked about variability from year to year. You know, El Nino causes variability from year to year. You also get other things that cause differences in the amount of rainfall you get in Murraylands, from year to year. But naturally occurring variability like El Nino, Southern Oscillation, and so on, there's also other sources of natural variability that occur on even much longer timescales. And so this is another form of climate variability, but this is on a much, much longer time scale. So this shows the concentration of carbon dioxide in the atmosphere. And it goes back 800,000 years ago to near present, to nearly up to where we are now, but not quite. I'll come back to that point in a moment. And you can see that there's lots of bumps and wiggles. So it's sort of, in some years it gets up to around about, at one point it got up to 300 parts per million, whereas another place it got down to about 170 parts per million. So you can see there's this huge amount of variability in this, in the concentration of carbon dioxide in the atmosphere. And it's all just from natural processes. So natural processes are really, really important, not just from year to year, but even on these much, much, much longer timescales. And you might wonder where scientists get this information from. And it's from taking ice cores in places like Antarctica. You can see an ice core there on the right. So in parts of the Antarctic, it's so cold, even during the height of summer, it's still well below zero. So that the snow won't melt from being heated up, but so it just accumulates year after year, century after century, millennium after millennium, for a million years. And as that snow builds up, the pressure gets so great that it actually does melt the snow underneath it, and then it freezes. And the air that's in the snow gets trapped in the ice. And so what people do is technicians is drill a hole down into the ice, and the further they go into the ice is effectively going further back in time. And then they extract the core, and then they analyze the air bubbles trapped in the ice core. And then so by doing this, they can look at, well, what was the concentration of carbon dioxide in the air bubbles going back 800,000 years ago. So that's why we have these very reliable estimates of what carbon dioxide's been doing hundreds of thousands of years ago. So the facts are that natural processes alone, like El Nino, La Nina and so on, and changes in atmospheric concentration of carbon dioxide drive changes in climate on all timescales. And natural variability is extremely important to climate in Australia, including South Australia. So that's the variability, but now let's look at how things have been changing. And so let's return to this plot here. So this is again the plot showing a time series of the concentration of atmospheric concentration of carbon dioxide. And that's what it was in the Antarctic, but carbon dioxide is extremely well mixed through the atmosphere. So this is not a bad estimate of what the global carbon dioxide concentration is. But I said this goes back from 800,000 years ago on the left through to near present, but not to present, to near present. And there's an important segment of time missing from this plot. And that important segment includes the period from the beginning of the Industrial Revolution. So let me now show you what atmospheric carbon dioxide has been doing since the beginning, or for the last 1,000 years, as well as since about 1780 or so, when the Industrial Revolution began. And I'll present it on the same scale so that you can compare it readily to what natural processes have been doing for the last 800,000 years. So there it is there. So that's exactly the same thing, the concentration of carbon dioxide in the atmosphere for the last, 2,000 years. So it's just a continuation of the previous plot. But then you can see the big spike up towards the end since the late 1700s towards record values. So we now have an atmospheric concentration of carbon dioxide above 400 parts per million, but we never saw anything like that during the previous period. And you can also see that the rate is extremely fast compared to it's quite a rapid increase in the amount of carbon dioxide in the atmosphere. And that's largely because of human activities where we've been burning fossil fuels. And the other thing that's been happening is that the world has been warming up. So what this shows, these little bars show the temperature anomaly, the globally average temperature anomaly of the Earth. So how warm the Earth is. So if the relative to our reference period, which I can't remember what it is, but some long-term average. And the blue indicates that the world was cooler than that long-term average. So there's a bar here for each year. whereas the reds indicate that the world has been warming up. And so you can see that in recent years or recent decades that the planet has been warmer than it used to be, and that the warming has continued. So there's been an upward trend in warming since around about 1970. But again, you can see lots of variability, but there's this prominent underlying trend in the average temperature. And you can also see the same sort of thing in, I probably won't embarrass myself by trying to pronounce this, Nuriutpa. Is that correct? Nuriutpa? Yeah.
Nuriupta.
Oh, yeah, not too bad.
No,
And
you're
again,
close.
eh?
You're very close.
Thanks. And this shows the mean temperature. Each one represents how warm the temperature was, the mean temperature averaged over the whole year for that location. And so you can see, again, there's lots of year-to-year variability. Some of that will be due to ENSO, but you can also see that there's been a warming trend. And if we go back to the previous plot, the Bureau has done that over the whole country for minimum temperatures and maximum temperatures. And then they calculate the trend. And if it's positive, they'll paint it pink or red. And if it's negative, they'll paint it blue. But you can see that everywhere across the country, for both minimum temperatures and maximum temperatures, they've all trended upwards, including, as expected from the previous plot, in your part of the world. So as the world's warmed up, Australia's warmed up, including your part of the world. And one thing that people sometimes say, oh, look, Australia's warmed up by, I think it's around about 1.5 degrees Celsius now since 1910. You sort of think, yeah, 1.5 degrees Celsius doesn't sound like a big deal. But actually, it makes a really big difference to how often you experience extreme temperatures. So this is an example of that. This shows that the frequency or the number of days Australia's mean temperature was in its warmest 1% on record. So you look back at the record, you say, okay, how often was the whole of Australia in that highest percentile? Really, really warm. So you see back in the old days, yeah, sure, it used to happen, but not very often. Then as time marched on, you can see that it happened more and more and more often. And this is what you expect from general warming. One way of thinking about it is that, say you have a bell-shaped curve, a normal distribution, and you move it, it seems like you're not moving it that much. But if you consider what's happening at the tails, you're really making a big difference to how likely it is you're going to pass an extreme temperature. It makes a really big difference by considering that the movement of that bell-shaped curve. So that's one reason why I think some people are a bit puzzled about, you talk about 1 or 2 degrees or 3 degrees, but it does have a huge impact on extreme, frequency of extremes and the intensity of extremes. And then the other thing is, say you had 4 degrees warming, well, you think, okay, 4 degrees seems not too bad, but then think back at the warmest day, some of the warmest days you've experienced, and add on 4 degrees, how unbearable that would be. That's another way of saying that, so we shouldn't get sucked into believing that just because it's 2 degrees or 3 degrees or 4 degrees, it's not a big deal. It can be a very big deal in some instances. So the facts are that the planet has warmed up and atmospheric concentrations of carbon dioxide are higher than they've been for at least 800,000 years. And so why is it that scientists link increases in carbon dioxide to global warming? And the answer is the greenhouse effect. And so what I'd like to do now, if I can, stop sharing so you can see me. And I'd like to outline the world's simplest model of the greenhouse effect. So let's suppose that you've got the sun up here and it's beating down with, it's called shortwave radiation. Let's say the bottom of my panel is the surface of the Earth. So the radiation comes down, gets absorbed by the surface of the Earth, and then the surface of the Earth warms up. Now, everything that warms up at the sorts of temperatures we live in gives off long wave radiation. Long wave radiation is invisible to the naked eye, but it's a very real form of energy. It's the sort of energy that's used in night vision goggles. They will detect long wave radiation, or heat-seeking missiles. They'll detect long wave radiation, adjust it, and try and blow things up. So the radiation, short wave radiation, comes down. We can see that, hits the surface of the Earth. The surface of the Earth warms up, and then it starts to give off long wave radiation to outer space, and then reaches a nice balance. It'll come up, as it warms up, it'll give off more long wave radiation, and then it'll warm up to a point where the amount of short wave radiation balances the amount of long wave radiation, so that there's a balance between incoming and outgoing radiation. Now, the trouble with that simple model is that there's also an atmosphere. So it's a little bit more complicated than what I just said. So, and the interesting thing is that the important thing is that the atmosphere contains greenhouse gases. And greenhouse gases, their crucial property. Hello there. Hi, Catherine's kid.
He's doing his homework.
Oh, right. Is he looking at climate science or?
No, he's not doing climate science.
Ah, that's a shame.
He is listening though.
Yeah, so the crucial feature of a greenhouse gas is that they absorb long wave radiation. So the short wave radiation comes down, the planet warms up, gives off long wave radiation. Some of that goes to outer space, but some of it gets absorbed by the atmosphere. And so because it's absorbing energy, it warms up. And so it gives off long wave radiation. Some of that goes to outer space, but some of it, and this is the crucial bit, some of it comes back down to the Earth, the Earth's surface. So the Earth's surface is receiving the short wave radiation, but it's now receiving this extra dollop, this second whammy of long wave radiation from the atmosphere. And what humans have been doing is increasing the concentrations of greenhouse gases. And so they've been increasing the amount of long wave radiation. And so because the Earth is receiving more energy, it warms up more than it would otherwise. So that's like I said, the world's simplest model of the greenhouse effect. And you might not be that impressed with that explanation, but because, I was hand waving, I assumed that the Earth was flat. I ignored the fact that there are clouds, that there are oceans. And so in order to understand what the impact of increasing greenhouse gases is on the climate system, you need something much, much more sophisticated, something that incorporates the details of the physics of the whole climate system. And that's exactly what we have. Remember, we were talking about the climate models that the Bureau uses to provide rainfall outlooks and temperature outlooks. Well, we can use those same sorts of models to understand things like, well, what happens if we increase carbon dioxide in the atmosphere? How does the planet respond? And so that's exactly what we do with in climate change science. We take those models and then we'll increase the carbon dioxide, and then we'll see what happens. The model will tell us what's going to happen to temperature, what's going to happen to rainfall, what's going to happen to ocean temperatures, winds, ocean currents, snow, lots of other different things. But in order to work out what's going to happen in the future, the models need to be told what's going to happen to carbon dioxide. And what's going to happen to carbon dioxide depends crucially on what our emissions are going to be in the future, what our global emissions of greenhouse gases are going to be, net global greenhouse gas emissions. And so what we do, climate scientists, is we look at different scenarios. Some scenarios we assume that emissions are going to keep increasing and we're going to get really, really high concentrations of atmospheric carbon dioxide, for example. Another scenario will assume that the Paris Agreement to reduce global greenhouse gas emissions is wonderfully successful, and so emissions come right down. And so we have much, much lower concentrations of carbon dioxide. And so then we just say, okay, if the world chooses to implement the Paris Agreement, so reduce emissions markedly, then this is what's going to happen. Or if the world doesn't, and we keep increasing greenhouse gas emissions, then this is what the world's going to look like. So we don't predict, we just say here is two different scenarios. And there are lots of different scenarios in between those two extremes. So what happens if we consider these scenarios? So we put in the increases in carbon dioxide under different scenarios, and we look at what the globally average temperature is. And this shows how much warming you get for each of those scenarios. So this is results from lots and lots of different climate models from around the world. And this is the temperature of the planet relative to what it was in the second half of the 19th century. So you can see that pretty much everywhere the planet is warmer than what it was back then. And you can see that what happens in the future. So this plot goes from 1950 through 2000, 2050 through to 2100. So you can see that we're sort of in around here. And then in the future, what's going to happen really depends on which scenario we use, what the greenhouse gas emissions are going to do. If Paris is successful, we'll be down here somewhere. If it's completely unsuccessful, we'll be up here. So we'll get an extra. So we're around about 1.1 degrees globally warming, so about here. So getting up to about another 4 or 5 degrees if it's very unsuccessful. Then you can see that if the Paris Agreement is successful, we get more warming, then it starts to level off and even comes down a little bit under some scenarios. So this is the sort of thing you can do with these climate models. So you get the global average temperature. And so this is showing that, that as the greenhouse gas emissions increase, the amount of warming of the planet increases. And another way of putting that, and then one point to notice though, is that no matter which scenario we use, we still get some additional warming over the next 20, 30 years. It takes a while for the scenarios to kick in, to have an impact on the global temperature. So a certain amount of additional warming and a certain amount of climate change is already locked in. There's pretty much nothing we can do about it. Now, the models produce global average temperature, but they also produce projections of temperature spatially. And so what this shows is the map of warming for 3 different levels of global warming. So the map on the left shows what the map of global warming looks like for 1.5 degrees global warming. So if the planet as a whole warms by 1.5 degrees Celsius, you can see that some places warm less and some places warm more. And you can, if we come over to the 4 degrees one, because some of what I'm about to say is easier to see. So the global average warming is 4 degrees, but the Arctic warms up a lot more than 4 degrees. In fact, all of the land surfaces warm up more than 4 degrees, especially the further you go inland. And we can also do the same thing for precipitation. We can look at what's projected for the latter part of this century, for 3 different warming levels. So if the planet warms up by 4 degrees Celsius, then we get this rainfall change map. This shows did you hear that? Did you hear that woman? Did you hear that? There's a woman who pretty much every night she drives a car quickly past and she bips a horn for her ex-partner just to stir him up. We don't know why.
I heard it.
Same time every night.
Virtually every night she does it. Anyway, so these show the projected percentage change in precipitation. So remember, with temperature, pretty much everywhere warms up, pretty much everywhere. Whereas with rainfall, some places the average rainfall goes up, some places the average rainfall goes down, depends where you are. So for example, near the equator, the rainfall goes up, in the Arctic and Antarctic rainfall goes up. But you can see over parts of Australia, it tends to drop, especially southwest WA. So these are the sorts of things you can get out of the model. And And that's for the average rainfall. So that's the long-term average rainfall. But you can also look at extreme rainfall, the sort of rainfall that we've been experiencing over much of Eastern Australia recently. And the models suggest that the wettest days are projected to become even wetter. And the degree to which they become wetter depends on how much extra warming there's going to be. By the way, the models suggest that the rainfall we're receiving, when we have those really heavy rainfall days, they're already a bit wetter than they would have been if the planet hadn't already warmed up by 1.1 degrees Celsius. is already about 7%. The wettest days, the highest rainfall is already about 7% wetter than it used to be. But if the warming continues up to, say, 4 degrees, then rather than 7%, they'll become 30% wetter. So, and you sort of sometimes you show this to people and say, yeah, okay, well, it's a bit unclear what that means. So to try and make that a bit easier to digest, what I've got here, which I presume is a bit close to where you both live, Mandy and Jane, Swan Ridge.
Yeah, it's more southwesterly from Paringa.
Right.
Oh, so it's basically south. Oh, sorry, it's southwest.
Okay.
It's towards Murraylands Ridge.
But not too far.
No, definitely not.
Yeah. So this just shows the daily rainfall at Swan Ridge from the Bureau. You can get this online. And back from about 1995 through to 2018. And again, as you can see, there's a wide variety of different rainfall amounts. But you can see that there's some real unusual ones, really high ones. So this one here, for example. So that's that's above 85 millimetres, and that's in one day. So that's a lot of rainfall for one day. And you've got plenty of these other ones around 50 or 60 millimetres, 40, 50, 60 millimetres. Again, even that's quite a lot of rain. When you have these really, really extremely heavy rain days, do they present problems for you or your community?
Well, they do from a farming perspective because crop losses, that sort of thing, where it's just like, for example, Lameroo the other day, 3 days ago, they had 60 mils in less than like half hour.
Oh, really?
And that just hammers the ground. It doesn't get the opportunity to sink in. It ruins the crop. Whereas a steady rain, you've got that absorption rate in the soils and whatever. Heavy rain just sits on the top, bounces off, and just cripples the crops.
Right. Thanks, Jane. Did you any impacts in your part of in what you do?
Sorry, my husband's just joined me, so now he's talking in one ear. You're talking
Oh, that's all right.
He's the actual farmer here. So, yeah.
Probably a similar story then if you're a farming family.
Yeah, definitely.
Yeah, no worries. All right, so this is the past, right? So this is what's actually happened. And so then we just looked at the projections, which were saying if the world becomes 4 degrees warmer, that the heaviest rainfall days, sort of like the heaviest you get every 10 years, that sort of heavy, then they're going to become something like 30% even heavier. So what I've done here is to, so that's what this is saying here, sorry. So it's saying that if the world warms up 4 degrees more, then on average, the 1 in 10 year event will become 30% wetter than what it used to be. And so to try and make that a bit easier to digest, I've just shown you what would have happened if an event like that occurred in the future in a 4 degree world. So yes, it would have been probably 4 degrees warmer-ish, and then the amount of rainfall would have, instead of it being 85, it would have been much higher off the scale here. So which presumably would, depending how that went through the day, would be even more damaging in some contexts. So what does all this mean for South Australia and the Murraylands? Well, fortunately, there's some great reports put out by, as I mentioned at the beginning, by the South Australian government, and you can get it through something called Climate Smart, I think it's called. Yeah, South Australia Climate Ready. And so the first thing this report says is that, and consistent with what we've just been looking at, South Australia is already experiencing the impacts of climate change. All of South Australia has warmed up since 1910. We saw that. And by the way, since 1900, winter rainfall has declined over most of southern Australia, and that includes parts of your region. There's the Pinaroo example with the trend shown. So yes, there's a trend downward there, but it would be virtually impossible to know I'd imagine to know that trend existed if you were just experiencing it, because there's just so much variability. And it's not a profoundly big trend at this stage relative to all of that variability. But the fact of the matter is, since 1900, winter rainfall has declined over most of southern Australia, but not all of southern Australia. And the other conclusion this government report makes is that the number of days with dangerous weather conditions for bushfires has increased across the region. That's referring to South Australia as a whole. The report then goes on to say that looking at the future, so that was the past, now it gives information about the future and what they project, and using the same sorts of models that we've been talking about. And this is a projection for the mid-century. So, projections will generally, if greenhouse gases are going to continue increasing, then these would underestimate what would happen after that. But this slide's just talking about mid-century. And so by mid-century, the following changes are projected. South Australia will continue to get hotter. Well, that's pretty clear from what we've seen already. And under a high emission scenario, remember we talked about how what's going to happen in the future depends crucially on what the scenario is towards the end of the century. So under a high emission scenario, something called RCP 8.5, South Australia can expect an average annual temperature increase of around 1.3 to 2.2 degrees Celsius, with a central estimate of 1.9 degrees Celsius. And these are all relative to 1986 to 2005. And by the way, Australia and the world had already warmed up by that point relative to pre-industrial. So these extra figures, the 1.9, you really have to add on that extra one, which is around about 0.6. So it's 2.5 degrees warming relative to pre-industrial. And not surprising, if you warm things up, that the number of very hot days, in this case defined as being above 40 degrees Celsius, will increase from approximately 2 days per year in Adelaide to 6 days per year in Adelaide, and from approximately 24 days per year in Coober Pedy to 46 days per year in Coober Pedy. And that's related to that argument I was talking about before, where you move the distribution. You end up getting extremes more often, and you'll experience temperatures you haven't experienced before more easily. And then it also talks about that by mid-century, under a high emission scenario, South Australia can expect longer fire seasons with around 40% more very high fire danger days. Sea level is projected to rise by around 24 centimetres along the South Australian coast. And by the way, I should point out that for some projections, scientists have much greater confidence than we do for others. So for the warming, there's very, very high confidence. For sea level rise, there's very, very high confidence. But for the details about rainfall in a particular location, long-term average rainfall, then confidence isn't as high. There's a degree of confidence that during winter, spring rainfall will decline, but that confidence is nowhere near as high as it is for, increase in the frequency of heat waves, increase in the temperatures that we'll experience and things like that. But there is more confidence. So there is a degree of confidence in that the rainfall events will become more intense and that's because as the atmosphere warms, a warmer atmosphere can actually contain more moisture. It has the potential to contain more moisture. So, the future atmosphere is going to be warmer, so it does have the potential to contain more moisture. And when that moisture, or water vapor, to be more exact, when that gets converted to rainfall, you get more rainfall. It's as simple as that. And finally, rainfall across South Australia is likely to continue to decrease in the future, especially in the cool season. However, and this is an important point, which relates to the first part of my presentation, that large natural variability exists. So yes, it's that the pressure will be on to reduce rainfall, but it's going to be embedded in lots of variability. So what you'll end up experiencing will be a combination of those two things. And then this report then goes, you can also get a report on the Murraylands, specifically for the Murraylands. And actually they talk about the Murray-Darling Basin, South Australia, the region indicated there, and I think you're both in that region. I'm hoping you're both in that region.
Yes, we are.
Yeah. And this is a great report. This is produced by, the South Australian government funded it. It was produced by the Goethe Institute, in association with CSIRO, the University of Adelaide, University of South Australia and Flinders. And I'll just whiz through some of this stuff. So they first talk about, by the end of the 21st century, average annual rainfall could decline by somewhere between 11.4 to 21.7%. Average annual maximum temperatures could increase by somewhere between 1.9, 3.6 degrees Celsius. And again, these are all relative to the period 1986 to 2005. So a little bit of a while ago, and warming had already occurred to that point. And average minimum temperatures are also expected to rise by something like 1.5 to 3.1 degrees Celsius. And again, I'll make the point that, it doesn't sound that much, but then think about some of the hottest days you've experienced during summer and add on 3.6 degrees. It's a more, seems more impactful.
We'll be hitting well over 50.
Yeah, well, what's your record, do you know?
I'm not actually sure, but I know we've hit like 48 a couple of times this year.
Okay, yeah, you probably would. Yeah, and that's the other thing. You because of the warming, you'll end up, I think I mentioned this briefly, that you'll end up seeing things that you haven't seen before, like, for example, temperatures. So one of the main points I wanted to make is that so you have to be careful about making plans that depend wholly on what you've experienced, because what you've experienced might not include events that are going to be as extreme as what they will be in the future. Sometimes maybe it won't matter for some people, but for some other people it will matter a lot. And then it talks about maximum temperature for the Murraylands. So climate modelling suggests that the average annual maximum temperatures could increase by up to 1.9, 3.6 by the end of the 21st century. The previous ones were for South Australia as a whole. This is for this particular region. And then it talks about, how if you reduce emissions, that warming isn't as great. And climate modelling suggests that average minimum temperatures could increase by up to 1.5 to 3.1 degrees Celsius. And it talks about how, if you reduce emissions, it won't be that high. And rainfall. Climate modelling suggests, so notice the word suggests, that relates to what I was talking about before, that the degree of confidence that climate scientists have varies from region to region, mostly varies from variable to variable. So for rainfall, for average rainfall changes, it tends to be not as, we tend to not to be as confident as, say, for temperature. But climate modelling suggests that the average annual rainfall could decline by up to 11.4 to 21.7% by the end of the 21st century in the South Australia Murray-Darling Basin NRM region. The last point I wanted to make was that for some, and it's an expansion of the point I just made, that for some things, for some contexts, maybe being 1.5 degrees warmer or 2 degrees warmer doesn't really matter. It's okay, it gives you more problems, but maybe it's not the end of the world. But for some systems, it makes a huge difference. And one of those systems is the Great Barrier Reef. So we know that this IPCC report, Intergovernmental Panel on Climate Change, they concluded that the majority of warmer water coral reefs, and Great Barrier Reef is one of them, that exist today will largely disappear when global warming exceeds 1.5 degrees Celsius, very high confidence. Reef restoration options may be ineffective if warming exceeds 1.5 degrees Celsius, high confidence. So in other words, there are things you can do to help the Great Barrier Reef, but if the warming gets above 1.5, it starts to become a bit like shuffling deck chairs on the Titanic. It's not going to really help. And then finally, the species and diversity of remaining reef communities are projected to differ from present-day reefs, very high confidence. So that's a very conservative way of saying that we'd be going from a Great Barrier Reef, which is highly colourful, a beautiful, biodiverse thing, which attracts millions of tourists, to something that's much blander, far less colourful, far less biodiverse. So this is just one instance where, yes, it does matter to, it makes a really big deal to try and reduce the warming as much as possible. So in summary then, we started off by looking at how profoundly important natural climate variability is to Australian climate and to your climate, and not only just from year to year or decade to decade or even generation to generation, but even on these tens of thousands of year type things. But then we also saw that in addition to all that really important natural variability, there's now an additional factor we have to take into account, which is human-forced climate change. And we've seen that it's already underway. It's not a thing for just the future. It's already starting to happen. It's going to get worse before it gets better. And how much worse it gets will depend upon what global emissions we produce over coming decades. So, and the greater the warming, the greater the associated changes. So remember, we looked at how much warming there was going to be, but we also looked at how number of days above 40 degrees. We looked at rainfall changes and how more intense, really intense rainfall will become. All of those things get larger, the larger the global warming is. And so clearly, markedly reducing global greenhouse gas emissions is a crucial thing to do if you want to manage climate change, probably the single most important thing to do. But the other important thing to do is to recognise that things have already changed and things are going to intensify before they get better. And so we really need to start to think about projections rather than just relying on what we've experienced firsthand. Start to also think about what the projections might be telling us and try and factor that into what plans we make. And it's very easy for me to say, but in practice, I think it's going to be extremely difficult for in some context to do it. That's what an increasing number of people and organisations are trying to start to do. And then the final point was that some systems, so something like the Great Barrier Reef, for example, they may go beyond management limits or their ability to cope if global warming exceeds some threshold. In the case of the Great Barrier Reef, it's 1.5 degrees Celsius, or 2 degrees, somewhere in between that period, that range. So thank you very much for listening.